Before the workshop starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
What we've seen now is we're able to get a rate of change at an instantaneous point, and this whole branch of maths then is called calculus. So if f of x is the original function, then this guy here allows me to get the slope or the rate of change at any instantaneous point. Okay, so keeping it general. We're now not at A, we're at any instantaneous point. And what we call this is f dash of x. Okay, f dash of x. And what we call it is, it's the slope function. So it's a function that will allow you to get the slope at any point. Okay, so I want to park that in your head because it's going to become more clear with examples, isn't it? Because we're a little bit theoretical at the minute. Okay, so then if f of x is the original function, then the slope at the instantaneous point A will be just putting A into this expression here, and this will get me the instantaneous rate of change at A. Now the process of finding the slope function, this guy here, from the original function is called differentiating, and f dash x is called the derivative. Now I'm only putting these up, I know for the children it'll be like, whoa, but it's because we're going to slip into starting to use this notation. They'll get comfortable with it after a while. Alternatively, we can use dy dx to represent the derivative of the function y equals f of x. So this is really just using the y instead of the f of x, but they mean the same thing, don't they? In fact, this one's nearly more intuitive because it's the difference of my y's over the difference of my x's. So it's very clear there that that is the slope formula. My first one here I have 4 linear functions. Okay, so you see the first function here, f of x equals 3. What's the slope of that line? 0. Perfect. Now, what's the slope of that line at x equals 2? Okay, what's the slope of that line at x equals minus 4? 0. Okay, perfect. What about g of x? What's the slope of that line? 0. What's the slope of that line when x equals 4? 0. Can you see where we're going with this? Okay, so looking at these three, we see that the slope of each of the lines is 0, and then the slope at an instantaneous point on the line is also 0. Okay, so what we're going to have is our function, and then we're going to look at our slope function. Okay, so just taking one of these as an example, I have f of x equals 3, and then what I saw was then that my slope at my instantaneous point was 0. So how I check that, if I'm looking for the rate of change at an instantaneous point, it's f dash. Okay, and when we looked at it at the point of 1, we saw that the slope was 0, isn't that it? If we looked at the instantaneous rate of change then at the point x equals minus 4, we saw it was also 0. And actually what's true is, if we looked at the instantaneous rate of change at any point along that line, they'd all be 0. Okay, so if my original function is 3, f dash of x, the derivative, equals 0. And this is why we call it a slope function. It's a function because if I put minus 4 in here, I get 0. If I put 1 in here, I get 0. It gives you a guideline for all of the x values. That's why it's a function. But that will become more clear as we work through the stuff, okay? So moving on, you can see your T&L is full of sort of tables for the kids to work through the stuff. Okay, we'll just move quickly on to the next one. So here's a set of functions. Let's look at the first one, A. Okay, what is the slope of f of x? What is the slope at the instantaneous point when x equals minus 5? 1. What is the slope of the instantaneous point when x equals 3? 1. Okay, so it's going to be 1 at any point along there, isn't it? Okay, so A then we have, so if f of x equals x, then f dash of x equals 1. Perfect. Let's look at C then. Or of x equals 3 over 2x, what's the slope of that line? What's the rate of change at the instantaneous point x equals 1? 3 over 2. Perfect. And it's going to be 3 over 2 at any point along that line. So let's have a look here. We just keep a track of everything that we're doing. So we have 3 over 2 x. So f dash of x equals 3 over 2. Okay. Then we have E. So what's the slope all along that line? What's the rate of change at this exact point? This exact point? Minus 1. Okay. So my slope function is minus 1. Now, sorry, this one's called g of x. So my slope function will be called g prime of x, or g dash x, and it's minus 1. Okay, so in terms of sort of checking out a pattern, we're getting a nice pattern here, aren't we, with regard functions of this type, where it is a linear function. So my slope function is just going to be the slope, isn't it? And we know the slope is always the coefficient of the x term. So it's going to be the coefficient of the x term when we are looking for the slope function. What about, let's look at B. What's the slope of that line? 1. Okay. What's the slope at this point? What's the slope at this point? Perfect. So, now having a look at this then, we have, for B we have wx equals x plus 2. So my slope function, w dash of x equals, as you just said there, it is 1. But then this is really interesting because when we did f of x in part A, f of x equaled x, and we also said our slope function was 1. How can that be? How can A and B have the exact same slope function? The constant, okay, so the constant goes to 0. Perfect. So you're looking at it from the point of view of wx equals x plus 2. So we saw that the answer will be whatever the coefficient is on the x, is a 1 there, isn't it? So it's a 1, and you said that the constant goes to 0. Okay, and that's what we saw back here, wasn't it? You're getting that from here. If it's a constant, it goes to 0. So you're sort of combining your observations. Very good. Okay. What about, is there any other way you could describe this? Why have they the same slope function? Yeah, absolutely. So another way of looking at it is B is the exact same graph as A, just shifted up to. So its slope hasn't changed. Sure, it hasn't. Okay, its rate of change has not changed. The graph has just shifted up to. So that's why we see that these are the same. So you've got kind of a dual one of an understanding here and seeing how the rules will come together as well. Okay, now as we said this morning, the lines are the easy ones, aren't they? What are the hard ones? The curves. Okay, so we're going to move up to the next one, which is x squared. Okay. And you're going to do an activity on this. So, x squared is really difficult. So what we're going to do is we're going to look for a pattern. So we're going to investigate what is the slope when x equals -3. So there it is. What is the slope at the instantaneous point x equals -2? What is the slope at x equals -1? And we're going to investigate, can you see there, 1, 2, 3, 4, 5, 6, 7. We're going to look at 7 different instantaneous points. Okay? And we're going to look at the rate of change at those instantaneous points. Now, remember on the Angry Birds what we saw? We can get the rate of change at an instantaneous point by getting the slope of what? The tangent. Perfect. So that's what we're going to use here. So see, we've one done out for you here. If I want to know what the rate of change at C is, I have my tangent at C, and I can use rise over run to figure out what is the slope of that tangent. So slope of that tangent there is -2. So I can tell that the rate of change at C is -2. So what you'll find is, guys, the rate of change at all of these points is going to be different. But what we're going to do is we're going to see, is there a pattern to it though? They might be different, curves might be awkward, but maybe there's some nice patterns within that to help us make sense of it. Okay? So I'm going to give you out this. It's the graph that's in the T&L, but I'm going to give it out to you on a printed out version, just so you don't have to draw on your T&L, okay? You see what you're doing now? I just want to mention something to you, because I think there is a misconception here that might happen with the kids. And now that you've started working on it, you might see what it is. It's this idea here of how you do the rise over run. Okay? Because the rise over run, it's pretty easy if your graph is increasing. Okay, if it's going up the stairs, your graph, it's pretty easy. So you're going across by your x value. Say you're going across 1 and you're going up by 3. Okay, so your slope is 3 over 1 equals 3. Now that seems okay, but what the student has to remember is you always have to read your graph from left to right, and you always have to do your x's first. Remember, the y's depend on the x's. You have to do your x's first. So when you've got a graph like this going down the stairs, you have to do your x's first. So what you do is you just pick a point on the line, just the same way as you do here. You pick a point on the line, you go across by 1 and up by 3. You pick a point on the line and you go across by 1. So you have to go that direction. And you see what happens then? Once you go over by 1, you notice, oh, my y's are decreasing. Do you see? So it is, your slope here would be -3 over 1, because the kids find it confusing. A, how do I draw that? And B, how do I get my negative slope? Is it a -1 and a +3, or what way is it? So they just need to remember the 1 will always be plus. It always has to be moving right to left. Is that okay? All right. It's quite a hard task, isn't it? Trying to see rises over runs when there's so much going on the page. But it's good practice for them to get out the ruler, hands-on, finding your rise over run. Really, really good practice. So what you did then, you had to then, what you had to do then was track your different instantaneous rates of change. So at A, when you figured out which tangent that was and used rise over run, we see that the slope of that is -6. Okay. Okay. Using the ruler again on the B, this time your rise over run was 1 and -4, so it's -4. Okay, C. You really needed the ruler, didn't you, to figure out which tangent you were looking at. You were given that one was -2. And don't forget, like if you download this back in the classroom, all these animations are on it and everything, okay? Then at 0 we have a flat ruler there, so our slope is 0. Okay, now coming over here on E, then we have rise is 2 and run is 1. So our slope is 2. And then our slope is 4. And then our last one, at that point, the slope of our tangent is 6. Okay. So now, we kind of knew, because of the curved nature, these slopes were all going to be different at the different points. But what we were curious about was there some sort of pattern in how the slopes were worked out? So what you had to do then was you had to plot all of your slopes. So what you're doing now is you're plotting the slope function. That's what you're plotting here. By plotting at -3, the slope is -6. When x is -2, the slope is -4. By plotting that, you're plotting the slope function. And using our patterns from Junior Cert, how we figure out the name of that line is, the slope of my function is 2. Perfect. Rise over run, we can see it's 2. My y-intercept is 0. So the equation of this particular function is y equals 2x. Absolutely. So my slope function is 2x. So what did I start with? I started with the function x squared. And I can see that my slope function is 2x. Okay. And again, I think this is really where you can see that this is a function, because my slope function is 2x. So let's have a look. Let's go back. Okay. When I put -3 in to here, I get the answer -6. That's what my slope is. If I put -2 into my slope function, it tells me the slope is -4. If I put 1 into my slope function, it tells me that the slope is 2. Does that make it very clear that this is a function to tell us the slope at any point? 1, 2, 3. Okay? It'd tell us the ones in between as well, wouldn't it? Okay. So that's really, I think that's very powerful for them. Okay? Now, you wouldn't really see the rule out of this yet. Sure you wouldn't. We know you just multiply 2 by the coefficient, but you wouldn't see that yet. They'd need to see more to establish that rule for them. So what you'll see is all through your T&L, it goes on to do 2x, 3x, 4x. They're the ones you can send them home with for homework, aren't they? Okay. Now we've a nice little Geogebra file here though for speeding this up, because like you want to let them get hands-on for one of them, but you might want to speed up the rest of them. Let's look at the function 2x this time. So we looked, or 2x squared. So we looked at x squared. Let's look at f of x equals 2x squared. Okay. Now, can you see here how we're going to be able to look at our slope function? My x value is -3, is on a slider. So I'm going to be able to come across and see what all of my slopes are as I move across. So I've -3, -12. Let's just look at this. -3 gives me a slope of -12. -2 gives me a slope of -8. Okay. 1 gives me a slope of -4. 0 gives me a slope of 0. So if -1 is -4, 0 gives me 0. Doesn't this make it much easier for continuing on? So at the point x equals 1, my slope is 4. And at the point 2, my slope will be 8, and so on. Okay. Now, what type of pattern is this? Well, what we did on the last one was we plotted it, didn't we? If we wanted to look at it another way, we could look at the change, couldn't we? So from -12 to -8 is +4, isn't it? So I'm +4 all the way down there, looking at my rate of change. I see my rate of change is constant, perfect. So what is it? Linear, perfect. And what is my rate of change? +4. Okay, so my slope is 4, and I'm going through the point 0, 0. So what is the name of this slope function going to be? 4x, perfect. So my slope function here, f dash of x, will be 4x. Okay, so you do enough of those. Maybe do one more until they get the idea of the pattern. Perfect. So I have my function, my slope function. We never really used the word slope function before, sure we didn't? But isn't it way nicer? A lot more understanding in it, especially when they get those questions. What's the slope of the line when x equals 3? It kind of makes more sense now. Okay, so we have got x squared and my slope function is 2x. So we have 2x squared and my slope function is 4x. We do another one, 3x squared, my slope function is 6x, and let them see what's going on there. So they might twig that they're multiplying the 2 by the 1, the 2 by the 2, and the 2 by the 3. But we know at this point we still don't have the full story, sure we don't, with regard to the behaviour of the tangents. So look, this file is brilliant. Look what I can do here. I can go in, just say I wanted to investigate 3x squared. I can come in here and change that to a 3. Isn't that brilliant? And now you can do the whole thing again for 3x squared. Okay? Or you could come in here and go, do you know what? I want to do an x cubed. So we really need to do an x cubed now to see what's going on with the powers, don't we? So if I wanted to put an x cubed in, so x hat 3, that's how you enter it in Geogebra. We'll talk about that a little more later if you don't remember. To put in a power, you just put in your wee hat. And now we have a cubic function. I'm going to zoom out a little bit so we could get a better feel for it. Okay. Isn't that great? And we can go through all of how the slope is behaving all along that x cubed function. Okay. So I'm going to come back here to my x cubed function. Right, this is it in the T&L. What you'll notice is we've given you a GeoGebra version of everything and a T&L version of everything because, well, if you're in a prefab and your internet's down and whatnot, you always have this version, get out the rulers, okay, or a homework version, get out the rulers, all right? What we did here, though, was for the x cubed graph, you'll notice we put the rise over run on every single one because it's too complicated to start getting into, okay? They just need to read it off. But this is the thing now, let's have a look at how these slopes are behaving. Here are my slopes, okay? And when I look at how they behave, look at the pattern of them. So what shape is that? It's a quadratic, okay. What is the name of that function? Any ideas? Okay, so it's an x squared shape. It's definitely an x squared shape. What you would say, do you remember your shifting and scaling? You would say the parent shape is x squared. Okay, but in an x squared, what is the point? When x is 1, what's y? 1. So what's this graph?
3x.
3x squared, absolutely. Look, when x is 1, y is 3. So you're right, the parent, it's absolutely x squared, but it's stretched out a bit, isn't it? So it's a 3x squared. So when we look at an x cubed function, we get 3x squared is the pattern of my slopes for my slope function. And you could probably do another one with them then for homework. And they will get 6x squared. So it's at this point that hopefully they'll start to see the pattern of what's going on. Okay, so what is happening to my powers when we look at this, when we make our slope function? Yeah, the powers are always reducing, aren't they? All my squareds went to lines. All my cubes went to quadratics. So you see that the power seems to always be reducing by 1. Even we can see it in the shape. Can't we? The cubic becomes a quadratic. And the cubic becomes a quadratic, and the quadratic becomes a line. So we're always shifting down a power. So we can see here that the story is that we multiply the power by the coefficient and we reduce the power by 1. Okay. So f of x equals x to the power of n. So my slope function would be multiply my power by my coefficient and reduce my power by 1. Okay. So that's nice, isn't it, that they would discover those rules themselves. So this is a question from the exam papers. So the graph of a cubic function f is shown on the right. One of the 4 diagrams A, B, C, D below shows the graph of the derivative of f. State which one it is and justify your answer. So you go for C. Okay, so park that now and we'll come back to this and we'll see if you're right on your C. Okay, things have changed though, haven't they? This is a huge, you can see now why you're trying to get them into the graph and the understanding and the behavior, absolutely. So just in light of this, we're not, for a start when we see this, we're not surprised that all the 4 options are quadratic, are we? No, because we've seen clearly now, when I have any sort of cubic, my slope function then is a quadratic, absolutely. And when I differentiate a quadratic, I always get a line. Perfect. I always get some sort of line. And when I differentiate a line, I always get a?
0.
Or a constant. Yeah, so I didn't leave myself enough room. I always get a constant. And then when I differentiate a constant, I get a 0. So we're looking at the progression of the shapes here. But now that's not enough. We need more information, obviously, don't we? Okay. So here's a cubic function. Okay. Here's a cubic function. If I look at this cubic function, what is the coefficient of the x cubed here? Can you tell by looking at it? Just, is it a plus or is it a minus?
Oh, it's positive.
Positive. So how do we know it's positive? Yeah, exactly. It's wherever it ends up, isn't it? So if it ends up going up, we know that this is positive. So it's plus x cubed model that we're working with here. Okay. Now, we're looking at the slopes here. Now let's have a look. Let's have a look at how they behave. We're going to look at how the slope of the tangent behaves. Now, at the minute, I'm going up the stairs, aren't I? Okay, so I have a positive slope. Okay. Now, as I move, can you see my slope is getting sort of flatter and flatter? So it's actually what you would say there is the slope is decreasing. Okay, your slope there is decreasing. Now, what happens when I get up to the top? What's my slope then?
0.
0. So my slope is decreasing, then it becomes 0. Now, can you see that my slope continues decreasing? It's kept going, didn't it? It kept decreasing. But now am I going up the stairs?
Down.
Now I'm going downstairs. So I'm decreasing, but I'm going down the stairs now, so now I have negative slopes. Decreasing, 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 but a little bit like the roller coaster, there comes a point where I stop decreasing and I start going back on the up, don't I? So my slope starts increasing now. Comes round the bottom. What happens here?
0.
0. And my slope continues to increase. Oh, now this is good. Now I'm going back up the stairs, aren't I? Now my slopes are positive. Okay. So let's look at that with numbers. Okay? Because it'll make it a wee bit easier for the students to understand. So let's put the actual slope on it. So now I have, it's very clear there to see I have a positive slope, don't I? Now can you see the slope getting smaller? Slope is decreasing, isn't it? Okay, so let's stop it there. Right, I have a slope and it's decreasing. Are you happy with that? I'm going to draw now the slope function. So it's decreasing. Now, what happens then? It gets to a point where the slope is 0. Now, where the slope is 0, where is my graph going to be 0? Well, I'm going to have to draw in an axis, aren't I? Because I'm going to have to make then a positive part of the graph, a negative part of the graph, and an equal to part of the graph. So this is equal to 0, isn't it, all along here? So isn't that part there? My slope is 0 right there. Okay. Then look, my graph continues to decrease. Isn't it? It's getting smaller and smaller, isn't it? And it's decreasing. So it continues to decrease. Okay? Now, look at what's happened here though. Do you remember going up along here? We were going up the stairs. And now we're going down the stairs. And that's because, look, all of these slopes were positive. They're all up in the positive part of the graph. Then once we got past 0, my slopes were going down the stairs. So these are all down here in the negative part of the graph. Okay. Now, there came a point, though, didn't we say, when we came down here and it stopped decreasing and it started increasing. So we're minus 5.4, minus 5.5, still decreasing, minus 5.77, still decreasing, minus 6, still decreasing, minus 6.25. Did you see that? Start going back up there, didn't it? It started going back up there. And that point, do you know what that point is where it goes from decreasing to increasing? What do we call that? Yeah, that point there. It's the point of inflection. It's where it stops decreasing and starts increasing. Now, that's a special point, the point of inflection. So now I've started increasing past that. So I was decreasing, then I got to this point of inflection, where I started to increase again. Does that make sense? But look, I'm increasing here, but I'm still going down the stairs, aren't I? So my graph is still down in the negative part. All my slopes are still negative. Okay? So I come around and I get to the point then where my slope becomes
Positive.
exactly, it becomes positive again. And right there at the turning point, it's going to be, my slope will be 0. So it comes up, my slope is 0, and then as you said, then it starts to turn positive again and continues increasing. Okay. Continues increasing, but they're all going up the stairs now, all positive slopes. So what we're going to do now is you can actually put a trace on, and this will actually plot exactly what I'm after doing there. So, can you see this? We're plotting, my slope is minus 14. Can you see we're up there now at At 14, sorry, my slope is 14, so we're plotting the slopes up at 14. So we're going to plot the slopes as we go. See? I'm decreasing, I get to my turning point, my slope is 0. I continue decreasing, I get to my point of inflection, and I start to increase. I get to my turning point, my slope is 0, and I continue to increase. So that is your slope function in the black. Okay. So to kind of encapsulate all of that, we have got some slides online. So this is under workshop 8, and what I just want to show you, it's under student activities, and can you see here it says sketching derivatives? Okay, so this is the next 10 slides are there. You can download them for yourself as well. Okay. So let's have the recap then. So this is my original function plus x cubed. Okay, so it's the same model as I did there. Okay, same sort of model. Now on my original function then, I am increasing. We call that at the top a stationary point. My function is decreasing, then I have another stationary point. And then my function is increasing. Okay, so that's the original function. Now, when we investigate the tangents, so we're looking for the slope function, I see my tangents are increasing all along there, aren't they? Slope values are, decreasing. My slope values are decreasing, and then all around here in the bottom, my slope values are increasing. Okay. So my graph really is split up into two by this point of inflection. Before the point of inflection, all my slope values are decreasing. After my point of inflection, they're all increasing. Okay? So what that tells me is that my graph split up into two, decreasing and increasing. So in terms of the shape of my answer, for my slope function, doesn't that tell me that it's going to be U-shaped? It's decreasing, then it's increasing. Okay? And a U-shaped, that's a plus x squared, isn't it? So this is going to be a nice guideline, isn't it? A plus x cubed, the slope function should be a plus x squared. Yeah, so that will give me one little help when I'm doing these type of questions. Okay? So it's going to be U-shaped. And because it's U-shaped, now I know that my point of inflection will be at a minimum point, isn't that right? If it was N-shaped, it would be a max. But I know now that my point of inflection will be a minimum. And the minimum will happen in the same place, at the same x value. Okay, it'll happen at that same x value. You'll see that now when we do a diagram. And what we saw was that my dy dx, my slope is 0 at my two turning points. Okay. So this is everything that I know. So when I come to sketch my derivative, let's say a freehand sketch, okay? Here's my slope function. The first thing that I know is that my two turning points are going to be the roots of my slope function. Isn't that right? So that's a good place to start. I know that the shape is going to be U-shaped, okay? And I know that my minimum is going to be in the same place as that point of inflection. So those 3 points will give me a guideline as to where to sketch my derivative, okay? So at this point in time though, we're not worrying about how far we go down. Okay, at this moment in time, this is just a freehand sketch of what we think the derivative will look like. Okay. So, as we said, as we were going through those slides, the slopes are positive. They're going up the stairs all along here in the yellow, so that means the corresponding part of the graph is positive. All of these slopes were going down the stairs, so all of these slopes are below the x-axis, and all of these slopes are going up the stairs, so they are above the x-axis. That will also help you sketching a derivative. See what are the slopes, okay? Are they positive or negative? Because it will give you an idea of where it should be above and below the x-axis. Okay. Now, the next thing you have to consider is at what rate is the slope function itself changing? Okay, so here we have that my slopes are decreasing. So the question is, how fast are the slopes decreasing? It's sort of like, what is the rate of change of the rate of change? So we're going here for the second derivative, aren't we? That's what we're talking here now, second derivative. How fast are the slopes decreasing along there? How fast are they increasing along here? So really what we have to do is we have to inspect the rate of change of the slope function. Does that make sense? You okay with this? We're going second derivative, so we're going to investigate slope function to find the second derivative. Okay, so here's my original, here's my slope function. Go at it again, and that will give me my second derivative. Okay, so there's my slope function. Now, for a start, this is a plus x squared. When I differentiate a quadratic, what shape will I get? A line, perfect. So we know it should look like a line. Okay, what do you reckon? A plus x squared, what type of line will it be? A positive, exactly. It's going to be increasing, isn't it? Okay. And then the other thing that we know is, if you look here, so the slopes are all increasing, which is exactly what we expected. You nearly know it's going to be increasing because it's a plus x squared. And then the turning point there, we know that the slope is 0 there. So that's going to have to be where it cuts the x-axis, isn't it? So this is what my line's going to be like. It's going to cut the x-axis where the slope is 0, and it's going to be an increasing line. And that is my second derivative. Okay. Now, this is where you can get a lot of value out of doing something like this, right? If we look here, here's them all side by side. Here's y equals f of x. Here's my original function. Here's my slope function. Now, isn't it obvious now to see why we put the turning points of the original function? We find them when dy dx equals 0. Isn't this the procedure? How do you find your turning points of a function? Get the derivative, put it equal to 0. Can't you see now why you do that? You're basically getting your slope function and solving for the roots. Okay. Then what do they have to do when they're finding the turning points? We have to decide which one's a max and which one is the local min. So what do? We get the second derivative. Isn't that the rule? So you can see here that when the second derivative is greater than 0, all up here, that is the one that corresponds to the minimum. And that's because, look, your slopes are increasing. They're increasing all around the bottom. Wasn't that right? So that's why it corresponds to this positive side of the graph. Okay? And then when dy dx is less than 0, that will be the one that corresponds to the maximum, because we were going down the stairs around here. So that's why we're down the stairs here with these slopes. But isn't that lovely to show them why you use those? Because they always seem counterintuitive, don't they? Less than 0 means max, more than 0 means min. It always seems counterintuitive, but I think that shows it very clearly why it is like that. Okay. And, okay, yeah, so, oh, and actually, do you know what else is there? How do you get your point of inflection? Yeah, you put your second derivative equal to 0. We can see that there. That's how you would get your point of inflection. Okay. So I'm going to leave that up there, and what I'm going to do is I'm going to give you a matching graphs exercise, and you're going to try and match the original to the slope function to the second derivative function. Okay? Okay, so there's your solutions, if you can see them. So guys, I think you can appreciate now how much the calculus has changed. Okay, a lot more around understanding and graph work as well with the calculus. But I guess things have been rolled back to accommodate that. So if you are an ordinary level Leaving Cert teacher, remember now that whereas you have to do this sort of understanding and graph work, you don't have to do differentiation from first principles. You don't have to do the quotient rule, the chain rule. Do you understand? So you're talking all the rules are gone where they were just sort of ploughing away. They didn't really overly know what they were doing. Okay? And now what's come in instead is a better, richer understanding of a rate of change and what it is, and then what they have to do is to be able to differentiate polynomials, okay, which they should be able to do out of finding out all their rules anyway, okay. And then it's been rolled back a little bit at honours level as well. They don't have quite so many functions to differentiate from, first principles, and they have to bring in their understanding as well. So why do you think it's C? It's a positive cubic. Okay, so that's the first one. It's a plus x cubed, so it'll have to be a plus x squared. Perfect. So that means it has to be either A or C. Okay, so we've eliminated to A or C. So why C? Oh, perfect. There's no maximum or minimum, so we are not going to have any roots. Perfect. Or another way of looking at it is the slopes all along that cubic, they're all positive. They're all going up the stairs, aren't they? So therefore, all of my slopes, my entire graph is above, all in the positive section. Yeah. Okay, so it's much clearer now. That's great. Okay, so what we're going to do now is we're going to go on to the more junior cert end of the school, and we're going to do a little problem. We're going to do a section now called problem solving as a means, not as an end. Okay, so here's the problem. John has 18 10-cent coins in his wallet, and Owen has 22 5-cent coins in his wallet. Each day they decide to take one coin from their wallets and put it into a money box until one of them has no more coins left in their wallet. When does Owen have more money than John in his wallet? Okay, so this is a nice little problem. You could give it out to a gang of second years, third years, fifth years. Okay, it's just a problem that you hand out. Now, I'd say it would probably be from second year onwards, okay? So the prior knowledge that they would be bringing to this would be an understanding of sets, number systems on a number line, order of numbers, all of their patterns. So all of their patterns bringing them up to y equals mx plus c. That's all of your first year work, and some linear equations in one unknown. Okay, so once you have that done and you're into the middle of second year, you could give them this problem to do. Also, what we would have done was some work on problem solving. So when you introduce problem solving to your first years or second years, we have this lovely poster to work with because we're trying to train them on different strategies, isn't that it? When you have a problem and you don't know what to do, what are the different strategies you can use to make a start on the problem?
Where did you find that poster?
So this poster is workshop number 3. Okay, so that's, it was handed out at workshop 3, and if you weren't in workshop 3, you could get it online and just print it out for yourself. Okay, so the first option was a student can do some trial and improvement on a problem. Or to make a start, they could draw a diagram. If they're just not sure what they're being asked, maybe it would be more clear in a diagram. They could look for a pattern. they can act it out, physically act it out and try and sort the problem out. Draw a table. That tends to be very good to organize your thoughts and to organize yourself if you're looking for a pattern. You could try and simplify the problem. Okay, so that's us looking for keywords and trying to simplify the problem as much as we can. Maybe we can use an equation. Maybe if I use some algebra on it, it'll make the problem easier to look at. I can maybe work backwards. And when working backwards, maybe I can eliminate different possibilities. Like when we did that calculus question, we were able to eliminate 2 straight away because they were a minus x squared graph. So it's that type of thing for problem solving. So maybe you would have that up on your wall, your problem solving strategies, and then let them off. Okay, so we're not going to explain too much about this problem. It's on page 1 of your workbook. And what I'd ask you to do now is, will you do the problem? So we'll go through the different strategies and see which one then that you went for yourself. Right. So the first one maybe is you could have acted it out. I definitely saw people doing this around the room, okay, because I saw people crossing off the 10s and the 5s on the page, and you're trying to act out what's going on. Okay? So we couldn't provide you with the money, but we provided you with a really nice picture, okay, to see if you would act it out. And I did. I saw people act that out. So as you were crossing them off, you were trying to see who, at what point would own have more money. So this is you crossing it off, okay? I guess you could give out the kids money if you had lots of it. Okay, but we see at day 15, it all changes here, isn't that it? Day 15, John has 30 left in his wallet, whereas Owen has 35 cents left in his wallet. So day 15 is where it all changes. Okay, if you didn't want to hand the kids out actual money, this is from one of the project schools where they just cut out little discs from paper and try to represent the problem for the teacher. Okay, so that's lovely. So that's acting it out. The other one then is, which I saw a lot of around the room, you simplified the problem and you drew a table. You know, try to contain your thinking and get some order on it. So I saw a lot of this, the table. So we started off, John is 180 cents and Owen is 110 cents. Now, did anyone do this? We've simplified the problem here by taking out the decimal, haven't we? Instead of saying €1.80, we've just made them all cent, because that might make it a wee bit easier to deal with. You don't have to do that, but it's a strategy to simplify it. And then as they put the money in, on day 1, John saved 10 and Owen saved 5. So on day 1, they have left in their wallet 170 and Owen has 105 cents left. Okay, so there may have been a misconception there, because by accident, couldn't you start day 1 as 180 and 110? You might get your numbering wrong along your table. So 180 is where we're starting, or if you wanted to put a numerical value on it, it would be day 0. Isn't that it, if you wanted to put it onto a graph? Okay. And so on. Now this is then a table. This is what most of your tables then look like. And it's a much better way of organising your work. Now this is from one of the project schools. So you'd be pretty happy if a student gave you that in second year. Like, that's really, really good. They've totally organised their work, and you can see here they have identified through their table on day 15, John has 30 cents, whereas on day 15, Owen is 35, and they have made their conclusion. So very, very good. Now, I did hear somebody say, oh, but now I have to do it the mathematical way. Okay? Now, do you? Is this done? It's totally done. Okay, that is good maths. Okay, so there's good logic and ordering and good maths there. So that is done. Okay, now another option then would be we could draw a diagram. Okay, so we could use a graph. And I saw, that's what I was saying, I couldn't have planted you better in the audience. So we have someone who did a beautiful graph there. And that's also a really nice way of looking at this problem. So John starts on 180 and he is reducing by 10 every day. And Owen starts at 110 and he's reducing by 5 every day. So what does the point of intersection on this graph represent? Yeah, the day where they have the same. And what day was that where they had the same? Day 14. So they had the same on day 14. And then after that, we can see that Owen has more money than John. How can we read that from the graph?
His graph is higher.
Yeah, his graph is now higher. Absolutely. So Owen's line was below John's the whole way until day 14. And now his graph is higher. His line is higher. So he's more money from there on in. Here's another one from the project skills. Okay, isn't this super? What if they identified on their line?
Slope.
Their slope, their rate of change. I think that's brilliant. So they have identified that the rate of change is minus 10 and minus 5. So that's particularly good. You'd just be delighted to see that. That's really, really good. Okay. So our other option then is we could have maybe made it a wee bit quicker by trying to look for a pattern. Okay, so if we were looking for a pattern, here's a kid's work from a project school. You can see this student went for the table, but then look at what they started to do over here. They started to look for the pattern. Look, what is my slope, my day, my start amount, and my total? Isn't that brilliant? This person, obviously, this teacher has done the money box problem with them and taught them their start amount and day 0 and taught them how to make a relationship between two variables for y equals mx plus c. So this student has brought this to bear on this problem here, and they've used it as a check for their work on their tables. Okay, so looking then at the actual patterns. So the amount in John's wallet that's left is he starts on 180, that's his start amount, minus his rate of change times the days. Okay, so that's in the form y equals mx plus c, isn't it? Or y equals c plus mx. And then the amount in Owen's wallet, he started with 110 and he's subtracting 5 each day. So those are our two patterns. Okay, and here we go. Here's somebody from a project school, and isn't it so cute with the label and everything? So this is brilliant work. Here's the slope for Owen, minus 0.05 times the days. Brilliant. Starting amount is €1.10. And when you take the €1.10 and you minus the 5 times a day, you get what's left in the wallet. So that's some brilliant work. And you can see a student like this, they're going to bounce into calculus no problem if they're doing that kind of thinking in first and second year. Okay, brilliant. So then we could also use an equation. So this is really how we're going to use our patterns, isn't it? When we get the two patterns, we can solve simultaneous equations to see on what day they had the same. Isn't that right? So if we put them equal, we will see what day the two boys had the same amount. So solving simultaneous equations, here we have John's amount. When is it going to be equal to Owen's amount? Okay, now I did this a little bit differently. Do you remember, it was workshop 5, you got a teaching and learning plan on equations. Do you remember we talked about the stabilizers? Okay, so this is just another way of doing equations if you're concerned that the kids are struggling with the whole idea of taking a number over and putting it as a minus, and then they're getting all confused in their rules of equations. This is where you just put your two stabilizers on, and you always have to do to the left what you do on the right. So the first one here is we're going to try and sort out the 110. So we're going to subtract 110 from both sides, and that way we get rid of it from this side, and on this side 180 subtract 110 will be 70. So we've reduced our equation down by doing that. Then what we're going to do is, looking at the minus 10d, what we're going to do is we're going to add 10d to both sides. Okay, so adding 10d to both sides, it gets rid of that on this side, and minus 5d add 10d is 5d. So now we're down to 70 equals 5d. What do I have to do to both sides now? I'm going to divide both sides by 5, and I have d equals 14. It's just another way of doing equations, but there's less chance of error because it's not quite as procedural. Okay, so exactly like you saw on your graph, then they intersect on day 14. Okay, so the remainder then that John has on day 14 is 40, and the remainder that Owen has then should also be 40. So Owen must have more money in his wallet after day 14, because they both save 40. They both have 40 left on day 14, but the very next day Owen's going to save less than John, isn't he? So you know the next day it's all going to change. Okay. And there's one of the kids in the project school. He did go for it like this. Okay. It's nice seeing the students work, isn't it? And all the different ways that they approached it. So what this particular problem is, it's a brilliant problem for bouncing into inequalities. Okay, this is what we call teaching a new topic through a problem. Okay, so the problem has lots of merit in its own right if we never did this. Okay, but now we can take it a step further and go into inequalities. Right, so if we look at our table here, what was happening on, say, day 13, John had 50 left in his wallet, whereas Owen had 45. And how we can say that John had more than Owen is, can't we use our inequality sign? So the greater than sign. And they will have that sign from first year. Okay, so that's greater than that. We saw through simultaneous equations and our graph that on day 14 they have the same amount, an equal amount. John is 40 and Owen is 40. And then it all changes on day 15, because now Owen is 35 and John is 30. So now the inequality sign changes because Owen has got more than John. Okay, do you see that? Right. So how can we use this idea of the inequality sign? Well, we have our two equations here to represent what John has left and to represent what Owen has left. Now what we did was we equated them to see what day they had the same amount. But actually what the question was when does Owen have more than John? So what we can do is set up a different type of expression. When does Owen have more than John? Do you see that? Just taking it that little step further. Okay. So this is called an inequality. When does Owen have more than John? But it behaves very similarly to an equation. Okay, so this is where it's very useful that we've already done the equation method. So very similar to an equation, we're going to subtract 110 from both sides, add 10d to both sides, and divide by 5 on both sides. And what we end up with is that Owen will have more money than John when the days are more than 14. In other words, day 15, 16, 17, 18. Isn't that really good? Like, look how quick that is compared to the table. This is where you get the wow of algebra sometimes. If they see a long way to do it and then they see this really short way, they go, okay, that algebra stuff makes light work of things. It's not any better, but it's more expedient. That's the thing about algebra, isn't it? Not any better, but more expedient. Okay. So own is more money from day 14 onwards. Okay. Now, seeing as we're here, we might as well take it a step further. What if I rearranged my inequality in a different way? So I started off with my question, when has Owen got more than John? But this time I'm going to treat my equation differently, because no two kids are going to do their equation the same way. Sure, they're not. They all kind of isolate different terms in different ways and at different times. So what if we tried to get rid of the 180 first? We would subtract from both sides 180. So that gets rid of that, and 110 subtract 180 is minus 70. Okay. Then what if the next thing the student saw was the minus 5d? And they go, okay, I'm going to get rid of that because I want my d's on the left. They do tend to take their stuff to the left, don't they? Their x's or their unknowns to the left. So if that's what they have in mind, they might say, I'm going to add 5d to both sides. So if I do that, I get rid of this 5d, and now minus 10d plus 5d is minus 5d. So now, minus 5d is less than minus 70. But what we have to do here is, if we have a minus on both sides, what we would typically do is multiply across by minus 1 and get rid of my minuses, which that's going to be fine in an equation, but in an inequality we're going to run into a wee bit of bother. When you multiply across by a minus 1 on both sides, we're going to have to change the direction of the inequality. Okay? And then we divide both sides by 5 and we will get the exact same answer. My days will be more than 14. Okay. So we see here that a little rule has come up. So nearly the exact same as an equation, except when we multiply or divide by a negative number, we must change the direction of the inequality sign. Okay, so why is that? So just if you ask the question, I have the statement 2 is less than 5. Now, get the kids to multiply across by minus 1 and talk to you about what's going on. So what's going to happen there? Yeah, you're going to have minus 2 is less than minus 5, and that is wrong, incorrect. So I think if you give them a few examples with number, they'll see why they have to change the direction of the inequality if they multiply or divide by a negative number.